We talk about precipitation reactions as one type. We're going to talk about the precipitation reactions, but we're also going to introduce this concept called net ionic equations. It shows up very prevalently with precipitation reactions, and so it's a good place to introduce this, but it doesn't necessarily, we can do net ionic equations for all sorts of aqueous reactions. So let's talk first about the difference between a molecular and a complete ionic equation, and then we'll talk about net ionic equation. In a molecular equation, everything is shown as bonded together molecules. So here I have silver nitrate, right? Here's my silver and nitrate ions, and it's shown as an ionic compound. It's a complete compound. We say molecular, but we mean they're shown as if they were molecules. And then I have sodium chloride. Sodium chloride as a complete ionic compound, making silver chloride solid and sodium nitrate. And if I study the solubility, it turns out that silver nitrate is soluble. It has nitrate ions, rule 2. And sodium chloride is soluble. Either by rule 1, alkali metals are soluble, or by rule, I think it's 3, chloride ions are generally soluble. And sodium nitrate, by rule 1 and rule 2, is also aqueous. Silver chloride is not aqueous. It's a chloride ion compound, but the silver is one of the exception rules, so this would make it solid. It's insoluble. So now that I know that, remember, if it is aqueous, we talked about when something is soluble and aqueous and it's an ionic compound, it will dissociate into its ions. So I can now make ions from it. So my silver nitrate actually is silver ions now separated and surrounded by waters that is separated from nitrate ions that are surrounded by water. So they're no longer stuck together as a molecular compound. It's now that crystal's been broken up. And then I have, same thing with sodium chloride, is really sodium ions and chloride ions. Silver chloride is stuck together. It is not dissociated. It is insoluble. So it would be one big crystal of silver ions and chloride ions all stuck together in a neutral crystal. And then I have my sodium nitrate would be sodium ions and nitrate ions. So the idea is in the complete ionic equations, I am going to show all aqueous ionic compounds as the dissociated 2 ions that it is made of it. And I might have more than one of them. If there's a subscript, remember when I break up the thing as a subscript, I may have more than one of them. So if I had 2 sodiums and a sulfate ion, so Na2SO4, and they were all stuck together. If it's soluble, and sulfates are generally soluble, and alkali metals are soluble, that would be a soluble compound. When I break it up, the 2 sodiums no longer remain stuck together. They never were. They were 2 positively charged entities. So I would end up with 2 quantity as a coefficient, sodium ions plus a sulfate ion. So you're not going to separate, however, covalent. Covalent, this is only ionic compounds dissociate. Covalent compounds do not dissociate, so you just leave them alone. Even though they're aqueous, you're going to leave them alone. And you don't dissociate any solids or liquids or gases. So if you made a product that was a solid product, you would leave it in its undissociated molecular state. So here we go. As a net ionic equation, I go one step further. I say, if I see ions that are appearing both as reactants and as products, then really nothing changed. If they were a reactant and they're still the same thing as a product, then there is no change. I call those spectator ions. We see in this particular example that I have silver plus ions that are not, but so I have my nitrate ion here and my nitrate ion here and my sodium ion here and my sodium ion here. So because they're both on the reactant and product side, they're really not doing anything. They're just kind of spectators. And when I have spectator ions, I can cancel them out and rewrite it without them. I can remove them from the equation to sort of clarify what's really happening here is that the silver ion, after it dissociated from the silver nitrate, and the chloride ion, after it dissociated from the sodium chloride, find each other and make a precipitate, the silver chloride solid. Remember, precipitate is just a fancy name for an insoluble ionic compound. So when I make it as a product, we call it a precipitate. So I make this solid, and that's really the heart of what's going on. So this would be the net ionic equation of silver nitrate plus sodium chloride making silver chloride plus sodium nitrate. So I want you to practice writing some net ionic equations. I have 4 for you here. Silver nitrate and we already did silver nitrate, but this is a different one. This is potassium chloride making silver chloride and potassium nitrate. Magnesium nitrate, and sodium carbonate making magnesium carbonate and sodium nitrate. Note that here I don't have states on them. I'm going to have to figure out which ones are the aqueous ones, which ones are the solid one. Here, I've kind of made it a little trickier. I've now given you names, so you have to convert the names into chemical formulas and then determine which ones are solids and which ones are aqueous, and then write the net ionic equation. And in this one, there's slightly harder compounds. They have some polyatomics in here and some Roman numerals in here. So again, convert the names into substances, into chemical formulas, and then figure out which ones are aqueous or solid, and then do my balancing, and then do my net ionic equation. So again, when I'm done, I can recognize a precipitation reaction from its net ionic reaction. Once I'm done, it turns out all of the net ionic equations for precipitation reactions are going to look something like a cation aqueous plus an anion aqueous makes an insoluble ionic compound. So cation, anion, ionic compound, solid. That's what we mean by precipitation reactions. Insoluble ionic compound is formed in the reaction. And the molecular equation is very often 2 soluble ionic compounds swapping anions. Remember, we talked about that type of reaction is sometimes referred to as a double displacement or double replacement reaction, when you have 2 ionic compounds swapping anions. So we see that generally precipitation reactions are also double replacement reactions. So here are some examples of double replacement reactions. In this case, we're talking about 2 ionic compounds switching anion partners. Here I have barium chloride plus silver nitrate. Notice that we had barium ion here and silver ion here. I still have barium ion and silver ion, but now here barium was paired with chlorine ion. Now silver is paired with chlorine ion. And here silver ion was paired with nitrate ion. Now barium ion is paired with nitrate ion. Notice that my subscript changed. That's because barium is a +2 charged cation and silver is a +1 charge. So when I repair them, I need different quantities of them. And I don't need to get too worried about the fact that this is not balanced, because balancing will come after I make up these products. After I find the products, then I'll worry about balancing. In this reaction, we have HCl and zinc sulfide, making zinc chloride and hydrogen sulfide. So I see that the hydrogen was paired with chlorine and now it's paired with sulfur, and the zinc was paired with sulfur and now it's paired with chlorine. Again, I see some subscript changes, but that's because hydrogen is a +1 cation and zinc is a +2 cation. So when I recombine them, when I swap, I'm going to have different subscripts. Use the charges to determine the subscripts, create the products, then worry about balancing. We can see this is how I would go about figuring it out. I recognize what ions I have, and then I need to switch. And then I'm repairing them, looking up their charges and using their charges to determine what the balanced chemical reactions, the product should be. Here I recognize what my ions are in the reactants. I swap them. I have to look up the charges of the ions so that I can figure out what the subscripts will be, and then I write the compound formulas. This is another example. This is sulfuric acid plus sodium hydroxide making water and sodium sulfate. This is not going to, so what would identify this as a neutralization reaction, or as a precipitation reaction, would be that I'm making a product. Turns out this is not going to be making a precipitate. It's going to make water instead. So this is going to be a neutralization reaction, but it is another example of a double replacement reaction. So I first need to identify my ions, and once I do, then I can swap them. I do need to figure out what my charges of all my ions are. Hydrogen is a +1, it's a group 1 metal. So hydroxide is a -1, it's a polyatomic. I know it has a -1 charge. Sodium is a group 1 metal. Did I say hydrogen is a group 1 metal? It's a group 1 non-metal, but it is +1. Sodium is a group 1 metal. It's +1. Sulfate is a polyatomic. It has a -2 charge. So when I pair these, that's where I'm getting this 2 from for the sodium sulfate. And that's why I don't have a 2. Here I had a 2, but I don't need it here because I just need 1 and 1. Note that when I come up with this, if I use a double replacement strategy, I come up with a formula of HOH. You need to recognize, yeah, but that's really water. That's H2O. So it's going to be written as H2O, but when you're doing double replacement, it makes more sense to treat it as HOH. So I can use the double replacement methodology to get the products and then recognize, oh, this is a neutralization reaction. Here again, I could have treated it as a double replacement reaction where this one's slightly different. This is not sodium hydroxide, this is sodium oxide. And in these, we really see that it's a very similar kind of reaction. I end up with the same products, but I had slightly different reactions. You do need to be careful. When we do double replacement reactions, sometimes we make a product that's unstable. There are 3 unstable products. And what that means is because they're unstable, they'll go on to react further, and these would be my final products. So if you were to make H2CO3, H2SO3, or NH4OH as your double replacement product, hopefully you recognize them and say, oh, they have to go on. Carbonic acid, H2CO3, makes water and CO2. Notice all 3 of them make water liquid, and then the remaining product is whatever was left. So water plus CO2, H2SO3 makes water plus sulfur dioxide, NH4OH makes water plus, this is ammonia, NH3. All of the other products are gases. So you do need to recognize these 3 as unstable intermediates. That we make them as a product, we can recognize in the double replacement that this is what gets made, but then they go on to react further. These would be what you'd put in your final formula as the products. Couple tips for double replacement. First, find the 2 halves of each compound. Then write each with a half with its charge on the right. Like switch the pairings, but just write the ions and their charges. Then use the charges to determine the new subscripts of the products. Then to check that there's a reaction, I want to get the states of everything. I have to be a double replacement, I either have to make a solid product, which would be a precipitation reaction, a liquid product, which would be water, or I can make some gases if I make one of those unstable intermediates. So I'm looking for the solubility, so I'm going to look at the ionic compounds that are produced. I'm going to look on a chart, and I'm going to look for, I recognize water would be liquid, but for the other ones I'm looking to see is it soluble or insoluble. If you make 2 aqueous products, it's considered no reaction. That's because if you write the net ionic reaction of it, and we'll do that in class, you end up saying that everything is a spectator on it, all cancels out. Therefore, nothing is really changing, no bonds are being made. It's not really a reaction. Again, watch for those unstable products. If you make one of those, you're going to break it down further into water plus whatever's left as a gas, and balance the reaction. A lot of times you're going to see polyatomic ions as the anion that's switching. If so, you can treat it as an element. It's a little bit simpler to balance. If I treat it as an entity all to itself instead of as its individual elements, it will still work either way. If water is made, you definitely you can consider it as HOH for purposes of balancing and for purposes of coming up with the products, but know that we would write it as H2O. Sometimes you end up with a metal that has more than one charge, like iron or copper or magnesium, well, not magnesium, manganese, vanadium, tungsten, cobalt, maybe not cobalt. So we have our ones that can have more than one charge ion. When I'm doing a double replacement, it's not going to change. So I figure out what it was as a reactant, and I'm going to keep the same charge as the product.